Okay, welcome to our next video on crystal systems. We'll be looking at cubic systems in more detail and putting some descriptors in place to things like points within the crystal system or unit cell, vectors to represent directions within the unit cell, and Miller indices to list planes that would be cuts throughout that unit cell. So we've seen unit cells before. As a quick reminder, we know that there are 7 different crystal systems. We'll be looking at cubic systems in this video. The crystal lattices, there are 14 of them. So within the family of 7, there can be 14 different lattices that are generated. And many of the ideas here for studying points, vectors, and planes, and the methods for naming these with syntax, if you will, can be applied into those other systems. Okay, so here's an arbitrary cube placed on the Cartesian coordinate system, x, y, and z. And we'll place the origin, of course, and we'll use the coordinates of the origin as default. So 0, 0, 0 represents the origin, of course. And if we want to list a particular coordinate within the cell, the unit cell, we make sure that we can kind of orient ourselves on the Cartesian coordinate system. So moving along the x direction here, this is the positive direction of that axis, as is this direction. And likewise up to the z label here, that's the positive direction. So a point of interest here, as you can see with our unit cell for a cube, lies in the positive, positive, positive space of the Cartesian coordinate system. So the one highlighted here with, say, a little box here for our icon, our point of interest, lies at a position that is 1 unit of A along the x-axis. A represents the length of our unit cell. It lies 1 positive unit of B along that y direction, and then it lies now up above that plane of the xy plane up to the point of interest here, and of course we have 1 unit of C in travel up to that final point of interest. So we originally traveled 1 unit of A, 1 unit of B, 1 unit of C for this ABC defined unit cell. And the point, of course, the point coordinates here are the 1, 1, 1 option here. We could also ask the question, where is the center of this cell? And so that's worth considering. So take a minute to pause the video and see if you can settle on that. Okay, so hopefully you're imagining a point in the middle of this cube. And so by definition here, we would have to travel to get to that x point. We would have to travel only half of the dimensions that we did to get to our 1, 1, 1. So a half unit of A, the positive direction, a half unit of B, again in the positive direction of y, and then up above that xy plane into the middle of the sphere now, with a half unit of C positive. So there, half an A, half a B, half an C, and our point coordinates are therefore half, half, half. Okay. So while fairly straightforward, we will build on this as we talk about directions and planes and consider accessing the negative territory of the Cartesian coordinate system as well, and representing the negative sign in our syntax for directions and planes. So in other words, it's very powerful to recognize that, one of the unit cells, like the one we've listed above here, is a representation by definition of units that are right in front of it, right behind it, to the left, to the right, and up and down. So that is any point that's in one cell. If it is in fact a unit cell, that point is twinned over in all the 3 directions next to it. And so we make use of that when we come up with methods for listing vectors and planes in these unit cells. Okay, so in other words, by translation, neighboring cells of that unit cell have identical positions or points or directions because that unit cell represents all units next to it. Okay. So crystallographic directions, these are a little bit more complex than the points that we just saw. Our instructions are listed here on what to do. So we're going to build a syntax that comprises square brackets and puts numbers in between those square brackets. So to build up towards this syntax, we've got 4 major steps to do. 1, we're going to inspect the vector in our cell of interest. And we need to ensure that the beginning of that vector, that is not the arrowhead, the beginning of the arrow, is crossing through the origin of our Cartesian coordinate system. So we see that here with my big red dot that I've filled in. Okay, so that beginning arrowhead, beginning of the arrow, the beginning of the vector crosses through the origin. If not, we need to consider a twin cell to the left, to the right, above, down, behind, and front to consider that same vector, but one where that does pass through the origin, okay? So this is the idea of repositioning, if you want, the cell to make sure that the vector of interest passes through the origin. Okay, in this example, we've got that, so no need for repositioning at the moment. Second, we read off the positions of the arrowhead in terms of A, B, and C. So very similar. So now we draw our attention to the arrowhead, and we now sort of do an analysis of how we walk over from the origin to that. So in this example, the first thing I must do to walk towards the arrowhead is I must travel in the positive x direction here, 1 whole unit of A. I then need to travel along the y. Okay, so notice x, y, z in that order. I need to travel along the y direction 0 amount, so 0b. And finally, I need to go up. In this case, we're pointing to a spot that's halfway up the cube. So we need to go halfway up the z direction, or a half unit of c, because we have a unit cell here defined by dimensions a, b, and c along the x, y, and z directions, respectively. Okay, so there we've now read off the projections of where the arrowhead is to get to the point of interest again right here. Okay, so in order to eliminate the sort of letters and move towards a syntax that only has numbers in it, we now take each respective coordinate, if you want to divide through by the A, B, or C dimensions. So this quickly modifies to a simplified version that is simply 1, 0, and a half. Okay. The next step tells us to adjust these numbers to the smallest integer values possible. And if you're handling a negative value at this point, you will move that negative sign above to create what's called an overbar. Okay, so at the moment we don't have a negative sign. We'll see that in the next example. But we can do simplification. So in order to eliminate the fraction, we do not want fractions in our syntax. We need to multiply everything by 2, the denominator in that fraction. So we will end up with 2, 0, 1 as our reduced form of the coordinates of where that arrowhead was located, representing the direction in this cell. Okay, and then the final step is to take that and put square brackets. Square brackets is overkill information. A bracket by definition is a square bracket. And we put brackets around that to finish off the exercise. So the vector in this example, that direction is the 2, 0, 1 direction. Okay. Perhaps you're considering, well, what about the information lost? We did a reduction, so is that still correct? Well, if you imagine another unit cell out front here, and we were to do the 2, 0, 1 direction, you would see that we would travel 2 cells over, reflected by the 2. We would go no directions in the y, so that is a 0, and then we would go +1, and we would get to the corner this time of the second cell over. So in fact, our vector does make sense by the syntax reflected through the 2, 0, 1 square brackets information. Okay, so that justifies the simplified version and the reduction that we did earlier. Okay, so this is one direction. When vectors on unit cells bisect atoms in the exact same way, many directions can be the same. So many directions can be regarded as being within the same family. So it's possible that many directions have the exact same populations of atoms along the direction of that vector, and we would represent all of them with now a pointed bracket, like a greater than or equals, or greater than or less than symbol, pointed brackets to show that. Okay, so let me just clean up the slide in case you want a more formal version of what we've offered here so far. Okay. In cubic systems, for example, it is known that the 1, 0, 0 direction has many other directions that have the exact same population of atoms along the way. So in other words, the family of 1, 0, 0 directions listed at right here is all equivalent to this 1, 0, 0. Another note, you'll notice that I have been saying 1, 0, 0, digit, digit, digit. I have not been saying 100. So in this syntax, we don't list 100 as the option. We list it by digit, so individual digits, reflecting the coordinate history that we've put into the mechanism here for the syntax here. Okay. You can see down here in our list for options that are within the 1, 0, 0 family of directions that we have some overbars. So here you can imagine that the directions here are accessing some of the negative spaces of the Cartesian coordinate system, x, y, z, that we're used to. Okay, here's another example. So here we're working our way backwards. So it asks us to please draw a 1, 1 overbar, 0 direction in a cubic cell. So we've got the steps here listed for us. Walking our way backwards now because we're given the crystallographic direction information, that is the syntax here. And now we need to draw this on a diagram. So our default diagram is below. We've got our cube, A, B, and C dimensions for the X, Y, and Z directions, respectively. And we know that we would sort of begin by taking the information in the syntax, spreading it across our table if you want. Ultimately, the overbar is going to represent a negative sign at some point, and we work our way backwards. So because reduction can't be predicted, we don't know what fraction we're handling here, so we sort of skip the reduction step, that was step 3, and advance right to thinking about how we take that information and use it to direct ourselves to the arrowhead from the origin. So you can see that overbar now is located as a -1 here on the central atom, and we've got a 1 positive on the sort of x direction and a 0 on the c, or the z direction. Okay, so it appears that we're going to need to access the negative territory of the y-axis. So we're going to be out in this area with our direction. Okay, so there's the next cell over. I know that my vector or direction is going to start at the origin. Okay, so I'll put a little dot there to emphasize that. And I got to access the space that is in this dotted enclosure. I got to access that cell somehow. Well, it looks like I'm going to try to position my arrowhead 1 unit away in the x direction. So 1 unit of A is my limit there, 1 whole unit length. Okay, so temporarily I'm over here. And then I'm going to go -1 on the y direction. So I'm going to now go over to here, getting 2/3 of the way along to positioning my arrowhead. And now I'm going 0 units of C up in the z direction. So I'm not going any further. So in fact, my arrowhead is going to be right here at that corner. And so this direction is right there. Okay. And we said earlier that we transmit or transpose unit cells to help us with our system to have an origin here. So you might imagine working our way backwards to sort of position an arrow in the actual box that was provided to us. And the final step is to take this vector and actually position it there. So arrowhead over here now, and we're going to position a perfectly parallel arrow here. And again, that is a twin to the cell and the vector that we've shown in the negative space there. Okay, so that's how we worked our way backwards. Okay, very good. So here we have the next example. Now we're moving forward. It's provided us the vector, and we're asked to provide the syntax for the vector that represents the syntax that represents the vector in this question. Okay. So take a minute to try this example. Again, pause the video to make sure you can do the work on your own, and resume the video once you've got your answer. Okay, so hopefully you've decided that we do not have a direction or a vector going through the origin, and so we again need to reposition this cube, create a twin to it to allow that beginning of the vector to be at the origin. So we're going to again access now the negative y territory. We'll consider now a vector starting at that origin instead, and so we've kind of considered an arrowhead now at the neighboring corner. And now the exercise becomes much more straightforward. Okay, so your coordinates for where that arrowhead is should have been 1 positive unit of A, 1 negative B unit along the y direction, and then 1 positive unit of C in the z direction, and then eliminating the ABC factors of the cell dimensions, we simply get 1 minus 1, 1. To reduce this, to get it ready for its square brackets, we now need to do something with our negative sign. And so reduction isn't needed, no fractions here. And now we position that overbar right over top of the middle coordinate for the arrowhead if you want. Okay, so we see that reflected here with the red line. Okay, so the vector that was provided to us here is the 1, minus 1, 1 direction. Okay. So here's another example where we're being asked now to consider this direction and provide an example. So the justification for the answer being negative 1, 1, 1 is again now recognizing that the start of our vector does not start at the origin, and we need to consider a neighboring cell that is a twin to this one and position the vector over there. So in this case, we're going to have to move into the negative x direction or space of the Cartesian coordinate system to help us. Okay, so we'll sort of consider a twin unit cell over there. Our arrowhead formally started here, but now you'll see by translating, we're going to position that there. So our vector starts now at the origin, and that means we would walk away to the furthest opposite corner in that cube, and we're ready to begin the process. So hopefully you can see here that our beginning information is -1a, walking now over, so that takes you to sort of the back corner here, then +1 over to this area, and then to finally get to where the arrowhead is, we have to go +1 to get up to that corner. -1, 1, 1. No need for reduction. We don't have any fractions, so no need to multiply through to eliminate fractions. And negative sign becomes an overbar, and so we have a 1 overbar, 1, 1, 1 square bracket syntax for the direction.